This is the Earth Science Classroom. Welcome back to the video. This is Metamorphic FACIES. Now, this is part of the rock playlist and Metamorphic rock video series. This follows on from both metamorphism and the process, what a metamorphic rock is, and also what the grades are associated with metamorphic rocks. Now, these grades will reflect this video and how we come to classify and identify these different facies within the metamorphic rock-like family. As we know, we're looking at temperature, pressure, depth. There's obviously a relationship between these, and how we go through different grades from low, being just above Diagenesis, to intermediate, to high. Now, there are various classic rocks that are linked with each grade, basically like, slate, going into, let's say, phyllite, going into schist, gneiss, and at the end, beyond that, metamorphic face is a sample of rock, right, that is consistent. So it's the same piece of rock that has certain or specific characteristics, and they are clearly identified, and they differ from other rocks, and they stand out, and they are distinctive, so you can see them. And these facies are basically the name for this distinctly different rock. They contain certain minerals that form within this metamorphic process or metamorphism at obviously the certain conditions, temperature and pressure at certain depths. And this refers to the physical conditions. So the chemistry of the rock and the minerals and how they're going to combine under heat and pressure and how they move based on their stability. They come under and they form a certain equilibrium at each temperature and pressure. So certain minerals and mineral complex structures will become very stable at certain conditions and others will not. So those ones that are stable will survive and be there and be identified as this obvious rock structure, and we call this a metamorphic facies. Now, there are the classic sedimentary facies based on depositional environments, and there is occasionally some igneous facies based on certain conditions. So if we apply this to a graph, and we have on the left hand side we have pressure in kilobars or atmospheres, we have our temperature up here going from basically the surface, the crust surface at 0 degrees Celsius, and we continue up to 800. Now, what happens is we have also depth starting again from the surface down to 20 kilometers and then 40. So we get a range of which these facies occur based on metamorphism and the pressure and temperature that each condition provides. Now, this dashed line right here, anything this side of the dashed line are conditions that don't apply or don't occur on Earth. So, for example, here at 12 kilobars of pressure, it's going to be around 275 degrees Celsius. That doesn't occur. It has to be a lot hotter at this depth and this pressure to exist on Earth. So you get certain conditions that do exist on Earth and don't, and this line's kind of separate. So the first one we've got to really add in is Diagenesis. So Diagenesis goes... Now, Diagenesis is the process of creating sedimentary rocks through layering, burial, sedimentation, lithification, and that happens at a certain temperature and pressure. So below 3 kilobars and below 200 degrees Celsius. Now, beyond that, we go beyond that, so it gets hotter and more pressure, we start to get the first kind of metamorphic facies that are a bunch of minerals that combine to make certain rocks that are particular and specific to that temperature and pressure. So the first one right here is zeolite. Now, zeolite is mostly hydrothermal. It's involved with more burial, and it's that first facies after Diagenesis. It is the first step in metamorphism, would have like a rock-like slate. It's to do with regional and low-grade metamorphism. It has certain minerals that create this zeolite facies. It's the starting point for all metamorphic conditions, both with subduction, with regional, and with contact metamorphism, has a normal geothermal gradient of around 30 degrees Celsius per every kilometer, and it is created over around 300 degrees Celsius, and between obviously 1 to 4 or 5 kilobars in pressure. The next facies is Hornfells. As you can see by the diagram and the graph, Hornfells covers a much broader spectrum of both temperature, especially temperature with a minimal range of pressure. So it goes from, like, let's say 0.5 kilobars down to maybe 2 or 3 kilobars in pressure. So it's going to be by the surface. It's going to be close to the, or within the crust, and is associated with mostly contact metamorphisms. So aureoles are going to form around it. So Hornfells is a general term for these various facies that occur in this temperature and pressure. Looking at pyroxene and hornblende as some of the minerals, looking at different starting rocks or perliths that can create the Hornfells, looking at mostly sedimentary rock as the parent rock, and you have different stages of these Hornfells based on the temperature and how much it's being burned by the contact metamorphism. This one is Blueschist down here. Now this one shows, again, it's like the Hornfells, but it's like the elongated oval, and you'll see that it's associated with higher pressure, lower temperature. So the temperature is going to be, around less than 300, but the pressure can be down as high as 10 kilobars. You have subduction zones as the main location, lower geothermal gradients, and this happens at greater depths between 20 and 40 kilometers. Even beyond that, we can get different facies being created, and also it kind of is formed after Greenschist, which we'll get onto in a second. So you just add in more pressure when that subduction slab in a convergent plate boundary is going down deeper and quicker through the pressures. So Greenschist, this is like the version of Blueschist, obviously based on the rock type, schist and schist, but it has different temperature and pressure characteristics and facies. So this is going to be a larger range, but it's going to be the normal regional metamorphism. Temperature range of between 300 to 500 degrees Celsius, pressure between 3 down to probably 9 or 10 kilobars, and the changing grade comes with the depth and temperature and pressure differences. So the minerals are going to be chlorite and serpentine, and most of the rock that creates this metamorphic facies is going to be basalt and maybe some andesite as well through different regional metamorphism locations. And this is our classic medium grade metamorphism. So looking at those phyllite, schist, and maybe even nice rock types. So if we're going further down into more of a higher grade environment, so above around 600 degrees Celsius and going from pressures of 3 down to 10, again, kilobars in pressure corresponds to a certain depth of between 10 and 30 kilometers under the ground, so still within the crust, mostly in continental crust. Looking at regional metamorphism, looking at composed of amphiboles and hornblende, and looking at the higher grades, looking at more schist turned into gneiss, and it's also a very coarse rock. So the final one in this kind of regional metamorphism stage, where you get the high temperature and the high pressure, higher temperature, looking at granulite. And this has basically looking at partial melting before anything solidus and liquidus line, looking at regional metamorphism, and looking at creating rocks of gneiss and migmatite at the highest grade environments, and can go down to really high pressure. All right, the last one to complete the Metamorphic FACIES series is eglitite. This is obviously a higher pressure, very deep down, looking at deeper intercontinental crusts, under mountain ranges maybe, or even in the very low lithosphere, and looking at various higher temperatures above 500 to 700 degrees Celsius. Again, looking at 3/4 of garnet, looking at the final kind of facies that metamorphic kind of produces or exhibits before it goes into just pure magma, goes back into the melting process. And this kind of completes the FACIES series, and you get the various rocks within this pattern based on temperature and pressure and depth.
This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.